welcome everybody in Ash's absence. I've just taken over secretary temporarily, but tonight we're welcoming Julian from Naval Tug to give us this presentation. So without further ado, I'll hand it over to you, Julian. Really appreciate you giving us your time tonight, and we're very excited to hear what you've got to say.
Okay, thanks, Hamish. Thanks for the opportunity to share what we do a little bit with you down under. Of course, we've got Mark and Tom running around for us there too. And we think also with recent events, with the Ever Given, now is also a good time to refresh what we've been up to and what we're doing. Naval Tug is a company that is owned by a tugboat operator here in the Netherlands. We operate in a couple of ports here. It's a small family business, and over the years, in fact, even since the 90s, we've been seeing that there's a lot of trends that show that as a tugboat operator, you would ideally have a better tool to look at what we're facing in the world of shipping. And now a tugboat, of course, a normal tugboat is there to enhance the port call turnaround of cargo ships. And the whole point is that cargo ships, when they enter a port, it's an environment where they don't want to be, because you have to sort of stop, which if you have a lot of mass, as you probably know, is a problem. But you also have to steer, because you get narrow and there's other traffic, and that's a sort of a paradox, because steering with the ship means not stopping. And so we've been taking our time to look at what we could do to improve that sort of port call turnaround, and ultimately that's where Naval Tug was erected, to use some of the technology that we thought might be helpful. So it's all about meeting today's shipping demands, as you can see. Why isn't it working? Okay. Yeah, so what we say is that there are 5 mega trends in shipping today, and that's been for a while, and these are the 5. You've got an increasing scale, particularly of container ships and cruise ships. There's a need for speed. Global supply chains want ever more speed into the trade flow. We see that safety has always been getting a lot of attention, but people are more and more about regulation and seeing how can we enhance safety, which is always a good idea. There is a lot of demand for more sustainable solutions. So just throwing power at the problem is okay, but everywhere we look, we see efforts to see how can we clean up, how can we make sure that we don't make a mess of things. And then, of course, there is the final trend of the demand for smartness. People are starting to realize that the internet and the way that everything is now connected and information can flow freely without cost also means that also industry starts to look at how can we use that to our benefit. So looking at scale, which is particularly important, we see that this is a picture of the container ship growth over the 50 years to 2018. Of course, there's a more up-to-date one, but we haven't had time to sort of in the recent events get a nice picture of. This is pretty nice, I would say. But by now the TEUs is 24,000. So the growth is ongoing, and I heard a number last week that only in the month of March, there's a lot of talk about, well, we need smaller container ships after the Ever Given, but only in March 45 over 20,000 TEU ships have been ordered from shipyards worldwide. So that is it's not about to stop anytime soon. There's over 500 of those vessels already floating, and counting. And the same sort of trend, growth trend, you see in cruise ships. This is a sort of the same period, looking at how the growth, compounded annual growth rate of cruise ships is about is even almost 9% year on year. Those are big steps. And at the same time, when you look at tugs for roughly the same period, you see that the way we solve things with tugs is static bollard pull. And if you look at how much has static bollard pull grown over roughly the same period, you see that the compounded annual growth rate of that is only just shy of 3%. And even if you would assume that given these larger ships, static bollard pull is a good proxy to solve the issues with those ships, which we think it is not. But anyway, even if you would assume that it is, then it's immediately clear that you're looking at a problem, because you cannot control on Earth, you cannot control something that grows with 7% or over, with something that is only growing at 3% over all those years. So the problem is getting larger and larger. At the same time, and this is also well known, the OECD has already analyzed that. Please let's please realize that global trade is dependent on shipping. That's what shipping is for. And what we're now seeing is a suboptimal solution, because whilst with these larger ships, you see costs of the transport leg of the goods drop. So the vessel, the costs of a vessel per TEU drops significantly when you get a smaller ship, a bigger ship. But at the same time, you see a counter curve for the handling costs of those ships in ports, having to do with canals, bridges, tugs, quays, container cranes, but also things like congestion and peak loads, right? If a 24,000 container ship would drop all of its containers at once in one port, you need basically almost 24,000 trucks to get rid of that, and that will clog the roads. And there is a lot of tail sort of economy hanging on to all of that. And the conclusion from this 2015 report of the OECD, and that's, again, that is already a long time ago, and the biggest container ship then was not even 18,000 TEUs, that we're already missing the optimum for the total costs of the transport chain. And that is, in essence, bad news for trade. The other thing, of course, with these large container ships is that, and I was in a webinar on Suez on Monday, and there were people from Egypt saying, well, you know, it's all fine. We hadn't had any accidents in the Suez Canal for decades, and we can't just, on the basis of a single incident, say that it's unsafe. I said, well, sorry, but this type of ship is a different job. It's not a linear function when you've got these huge ships that are 400 meters long and 80 meters high from the water, 400 meters. So that's basically a sail of about 3 hectares. The wind also starts playing a real factor, and you get drift angles, and the width of these ships then becomes easily twice as much, because it's you know, if there's a drift angle with the ship from the port side to the starboard side, ultimate point is not in the case of the Ever Given 59 meters, but around 100 meters if there's a 5 degree drift angle. And then, of course, your margins become really small, and there's no room for error. This is a picture of the CSL Jupiter that ran aground in a similar incident in 2017 on the River Scheldt, which is right on our doorstep. In fact, the shareholders of Novatug, the towage operator Multiship, we were the ones to take this ship off that slightly hairy position there. And you can see the port of Antwerp in the background where you immediately take in the problem. Well, this type of ship is so big that you can actually block in and outflows of ports. And in fact, that's also what we've seen a couple of weeks ago with the Ever Given. And one thing is now clear: these ships cannot turn around in that sort of area. This is another picture of that same incident where some guy thought it was a good idea to stand under the anchor, talking about safety, but it also gives you an idea of how that vessel ran aground on the bank at 14 knots, and it just shoves itself right high up the beach. And these sort of accidents fit a trend. We've compiled a little video of the accidents of the last couple of years since 2017. There is, of course, the added fact that everything is filmed nowadays, so all these accidents are actually in view. And then you see, well, it's kind of, and there is a tug attached, but it cannot really do anything. This was in Dubai in 2017, where another container train was pushed over by a container ship that was not under control. And it just now missed that building, and you can see all the people flowing out. This was in Venice in 2019. And again, cruise ships have a bigger problem even. This was in Antwerp in December 2019, where yeah, another container crane had to sort of hit the ground. And this is in Italy in 2018, I think. So, and these things didn't used to happen. This is cruise ships again, very hard to control in big winds because of the wind surface. And this all confirms to our idea that what we've already known is that tug demands should not be static as they are, they should be dynamic. We should be looking at a tool that can actually help when ships come into port and slow down, help up the steering at relatively lower speeds, whilst at the same time allowing the vessels to keep as much speed as possible until they need to slow down, and then indeed slow it down quickly. We've used that sort of input to think about, well, what could we do with the things that we understand to get a tool that would be able to assist here. And there again, it is not, I like to say, well, this is not a competitor to tug, it's a competitor to fixed port infrastructure investment, because when you see ships that visit your areas are bigger than what the area or the infrastructure was actually meant to take, you can do either of two things. You can enlarge the infrastructure, which is usually very costly, very time consuming, or you can try and increase the control over those ships within an environment so that they really don't need as much room as they normally do. The basic working principle of our system is that we've put the tow point on board of the tug, not on a fixed point, which is the regular situation you see on the right of the image. But we've put it on a ring, like a big ball bearing, which if the line comes perpendicular to the tug, the attack point of the force on board of the tug also moves to the side. And what you then get is that there is an automatic alignment between that attack point and the center of gravity on board of the tug, in line basically with the vector of the force. A normal tug, when the line goes sideways, the tug runs a very big risk of toppling, because the attack point of the force is in the middle and the line is up, the central point of gravity of the tug wants to align with that attack point of the force, and then you go much too much list on the tug, and then the water grabs the surface of the deck and the side, and it basically capsizes. And ours doesn't. And that means that you can actually, well, this is another picture, but it's not so relevant. You can actually get lift from the hull of the tug to do what the tug is for. You actually can use the energy of the tow through the by harvesting that energy basically for the thing that you need to do. That's either stop or steer the tug, the ship that you're assisting. And what that looks like is this, like this. And you can see we put the tow point on this ring, and if the tug goes sideways relative to the line, you increase the drag of the tug, and it's like a bucket behind your ship. You stop the assisted ship if that is what you want to do. And this allows you for an enormous freedom of movement. And the captain doesn't need to be so aware of keeping the angle of the tow line always in line with his center line of the tug. And here's a good view of what you can then also do. You can brake and push at the same time. And brake from forward to, this is the Australian slide with the no worries. And this is what that looks like in an actual operation, braking from forward and using the tug as a sort of a spring lead to help the vessel turn around. This is in Rotterdam, where this ship needs to do a 180-degree turn. And this is actually a very effective operation. And if you look at this, it doesn't look so dramatic, but there's 80 tons on the line at this moment. The vessel is doing about 6 knots. And you can actually brake from the forward and help steer as a sort of a fixed point in the water for the ship to turn around on. And there should be some drone shots here too. Hopefully we're getting that. Where you can see the turning, you can see the wash from the vessel, that it's actually, even though it is quite forward and the turning point of the ship is also quite forward, you can see it hopefully too. Yeah, well, that wasn't perfect, but sorry about that. And this is an operation that we do quite regularly with this boat, and this has the added advantage that you're actually also assisting the ship within its own length. So you don't need, like ports with turning basins, you don't lengthen the combination of ship and tugs so a 400-meter ship would typically become almost 600 meters with tugs front and aft. And here you can actually safely go within the length of the ship you're assisting. So you reduce that combination length typically to just the length of the ship. And here you can see it from the bow. You see the wash off the bow. The speed, of course, is not of the assisted ship. The speed, of course, is not very high, but you can see that it actually moves sideways. Another thing that we're doing is we measure everything. So we measure everything on board of our tug because we want to know how much energy do we basically add for the pool that we generate. And this is an assistance example that we then, so we get for every assistance, we get basically a data dump where we can analyze, well, what happened during this assistance. And this is an assistance that we did in November 2018. The ship, you see what the sizes are. And then we get from the ship's system, we get a readout of, well, what happened with all the parameters that we're interested in. So the top line is very small, but over the timestamp, we get the speed over the ground during the assistance, we get the tow line length, we get the tow line force, which is the third line. So you see in the middle, in the green bit, you see 40 to 60 tons generated. Then underneath that, you see the tow line angle. So that is, in that green bit, you see 90 degrees. And then typically, below that, you see power 1, power 2. So that's the two engines that they are basically idling. The engines are idling, and we generate 60 tons with next to nothing in terms of added power. And we also get a track of where the ship, this is the port of Rotterdam, this is where that assistance was done. And you get a place to see, well, we left the berth for the tug, we picked up the ship, and that's where we dropped it off. A big thing of that is or a big thing of our system is that you basically don't add energy for the problem in the opposite direction of the problem, but we basically use the energy in the problem to solve the problem. And that makes for a big drop in energy demand. And if you're talking about a diesel driven tug, which most of the tugs in the world are, this also leads to less fuel and emissions, of course. But the bigger issue there is also that it allows you to so we're talking about a very significant saving, like a typical for assistances, you can see up to 60-70% of fuel savings on when there's force on the line. And that means that it's easier also to electrify this operation, because the problem with electrifying tug operations is that the tugs just need an enormous amount of energy in reserve to when they generate the forces on the line with engine power, and whether that is a diesel engine or an electric motor or LNG driven engine, doesn't really matter. It's about the kilowatts that you need to generate line force. And if you do not generate the line force with the engines, but rather with the resistance of the hull through the water, you can easily much faster electrify, and that is so very that's what we're looking at right now. In fact, is to show that the iteration of the Carrousel Rave Tug that we built, the ones that you saw in the videos, is actually quite a big tug optimized for harbor services, and we needed it to also have 70 tons of static bullet pool, because otherwise we couldn't be operating in the ports that we wanted to show it. But really, that tug almost never uses its full engine power. It's mostly at idle speeds, 500 revs, working with very low added energy. But the way the regulations are now, you have the only metric is static bullet pool, and we're saying, well, maybe there should be also a metric showing how much energy you need for a ton of line force. And typically, and these are the pictures, we are a tugboat operator, so we've also got the standard ASD solutions, and then you see, if you look at these sort of picture, you see what sort of difference you're talking about in a certain operation here, the braking. So if we need 40 tons with the CRT, it's only 1,200 horsepower relative to 3,600, 3 times as much for the ASD. And you can see what in the water. You can also see what you can also see why. Another point is that if you increase the control, you can load up the available capacity much more efficiently. The weather and tidal windows that exist in certain ports can also be widened or even disappear completely. So you've got a much more much bigger operational envelope for the port and terminal facilities that are there. You could also say, well, this is such a powerful tool, I need less tugs. So also from a tugboat operator's perspective, you can say, well, I can do with less capex. And this is, of course, a big thing. This is another one of those accidents. This was in February 2016 on the Elbe in Hamburg, where this ship, one of the biggest at that time, it was also over 20,000 TEUs, simply had a rudder failure of 12 seconds and it was immediately aground. 12 seconds was the rudder not operational, and she ran aground. Of course, on the Elbe is a river. The port of Hamburg is 80 kilometers inland, and you have to steer on this river on the tide with a ship like this. And with the tide, of course, you've only got 6 hours to get there. And you have to really, really speed up. So these vessels go with 18, 19 knots. They go onto the river. And if they then have a slight hiccup, then they're immediately aground because they go so fast and the room is just very limited. And in fact, the funny thing is, with our Novatug website, we also have a page where we show all these accidents, and to raise awareness of, well, this is not a black swan once in a lifetime event. This is actually a structural problem with these enormous ships, because the infrastructure around the world is just not ready to deal with these. And we were, after the Ever Given incident, we were the world #1 for Ever Given incident. And that's not because we had already added that one incident in Suez, but on the Elbe in February 2019, this same Ever Given ship, which was then not even a year old, ran over a ferry on the Elbe in side wind in its dubious speed range, where it was speeding up to its service speed, but it was only running at 12 knots then, similar to the Suez case, where they had a side wind and they basically drifted over this ferry, not being able to control its heading well. And there was a tug there, but at that speed, of course, normal tugs cannot do anything anymore, unless you have specialized escort tugs with 10,000 horsepower and a lot of room again to deploy those. Well, this is basically what I wanted to show, and if you have any questions or comments.
That was great. Thank you, Julian. I had a little question. How does that help you operate better open up the tidal flow window? Is it just because you can achieve more braking and steering power in different current, or how does that really help you?
It's just the fact that the tidal windows are geared towards, well, if you are close, we need some sort of margin. And we say, well, if your control is better, you need less margin. I mean, you can redefine what the margins are. And we did an exercise back already 15, 16 years ago with then P&O Ned Lloyd. We have a port near us flushing, and the port entrance has a certain width, but the deep channel is a little bit less wide. And so that port had for container vessels a tidal window, because they weren't sure. I mean, it fitted also at low tide, but they weren't sure whether they could control the ship at slower speeds enough to be able to go in. And this is the relevance of this technology, is that you can actually, it is a rudder, right? So the problem with ships when they slow down is that the lift force of the rudder decreases, but also the arm on the turning point decreases of the rudder. And so the faster a ship goes, the better it steers, but the slower it goes, the worse it steers. But if you put this tug at the aft, you get more arm, and it is itself a rudder. So the CRT is a rudder with its own wing profile of its own hull. So you get quite a large rudder at a lot of, the longer you make the tow line, the more arm you have on the actual turning point of the ship. And so you can control the ship very well. And we said, just as an exercise, we said, well, we think we've got technology that we could open up the tidal window for you. But then what you would have to do is increase the strength of your bollards, because this thing will pull really hard. And so what I would like to know, I told them, is what is the cost of refitting stronger bollards on a container ship, and what is the benefit of having no tidal window in this particular port? And they said, well, that's quite easy. If we've done some calculations on a new ship, the cost of extra strong bollards is zero, because it's just a little bit of steel, and it's on the build of a ship. It's not a significant number. It's just on an existing ship with bollards that are not strong enough, that would not be strong enough, we would have to reinforce those, and that would be around 100,000 euros at the time for doing that for the whole ship. Now, on the other side, they say, if we miss our tidal window, we lay over 6 hours, and then we miss our slots, not only in this port, but also in the other ports of call, the subsequent ports of call. And a typical cost for us to miss our slots for an entire rotation is 300,000 euros. So they said, if we would be able to in agreement with the port and everybody else to go in at any tide, this would potentially pay out immediately, because we would do that immediately, because the cost of missing our slots is just very significant.
Wow, that's really interesting. Thank you.
Okay.
Julian, with how many tugs have been built, and what class are they with, and how did you demonstrate? I'm assuming that class rules normally wouldn't have covered that sort of arrangement, that sort of towing arrangement. How did you convince the classification society to sign it off?
Well, a good question, thanks. So we have been working with a prototype since 2002. We've been we've been working to understand the technology, to know its limitations, to know and we've been sharing that knowledge and data also with, and at the time in 2002, when we did the refit of an older tug with this ring, we were given permission by the, now class societies also run the shipping inspection for this government. But at the time they had their own experts, and they said, well, this is such an important safety feature for a tug, because you can't capsize the tug anymore with tow line force, that we allow you to do this and share, the experience and the data. And so we did that, and we shared all of that also with when we did. So we did about a decade of well, thousands of real jobs with this old tug, where it's a 1961 built tug that had a certificate of 21 tons. And we did 140 tons on the load line with that. And we completely safely, completely controllably, and we, with all the experience we built up, we started making a sort of optimized system, which this CRT is, and that is fully scalable. So the ones that we've got now are 2 in this size to be able to show them. But in that project, we went to Bureau Veritas, so BV is the class society, and because they had already been working on stability rules for tugs, they said, well, because of this capsizing, this girting problem, we are going to take the lead in devising stability rules for tugs. And we said, well, with our dynamic tow point, this is not a problem. And so we had a lot of sessions with them, and indeed they were forward enough to say, well, these stability rules, we will give an exemption to those tugs that have a dynamic tow point, because we understand this. And then they said, we will give you 20% extra room on the stability. And this was not a fun conversation from my end neither, because I said, well, why 20%? Why not 18? Why not 17? Why not 25? Because the problem you're defining is simply not relevant for this technology. And they said, well, we know, but this is what we're going to give you. So it was and this is typical. Well, dare I say it, engineers. they want to. Everybody holds on to what they know, and there's very little imagination, I would say. Because I had the same discussions with Robert Allen, who basically, Robert Allen is the one that basically designed the tug from a design perspective, and we also had the good fortune to work with Oscar Lissagor there, who did the hull resistance. And Oscar is the type of person that is different. He will just say, well, this is going to be a very powerful tool, and we're going to make it as slender and as low resistance as possible. So ultimately, this is what we ended up with. But you're right, because we worked towards a smaller iteration, and we say, well, the propulsion is not side by side, but in line. There are a number of reasons for that, but one of the benefits of that, of course, is that your drag also reduces. You don't have to make it as wide, and in the smaller version we bumped into the same problem. And then the 20%, because on this size, with the fact that we were aiming for a static bollock pull of 70 tons as well, ultimately 20% was enough, but the conversation wasn't finished. And now we with this smaller size, we ended up on 21, and then they didn't allow it. So I'm still having the conversation, actually.
And what about strength wise, as far as the actual tow point moving around that ring? How did you convince them of the strength side of things?
And this is what we already did at the time, because when we did the prototype 20 years ago, we were also wondering ourselves, how does this work, and how can we? So we did a lot of finite element calculations on the strength. But the point is, and we measure everything, and the point is that because this is a ring, and you spread the load very, very nicely, actually. So it's spread quite easily over the ring that we've got on these boats. Has a diameter of 11 meters. So half of that is the load-bearing side. So if you pull the ring, it's more a belt than a ring. So when you pull it, you pull it onto its wheels that all start bearing the load, and you spread it quite nicely. So it's actually much more it's not a point load, which a normal tow point attachment is. And this is like a ski. You know, you spread it over a long surface. And that actually works towards it. It's very elegant also from a mathematical perspective.
Yeah. Thank you.
Hello, Julian.
Hi.
James here. Thank you for that interesting talk. I was just wondering, do you have any carousel tugs operating in Australia?
No, not yet, and we're working very hard. Mark, also on the call, is working very hard to make that happen. But as you know, well, I'm a lawyer, and this is a regulated industry, and you have to show it and talk to regulators and show that what you're doing is actually makes sense. But it takes a long time. Shipping is a strange business. It's full of people that think that everything has been invented already, and that a larger ship is just the same but larger. Where we say, well, you know, these are non-linear relations, and you have to sort of get this, and the safety side of our system is also, physics always works, right? So it's very hard to get people thinking.
Yeah. Just as an aside, our section visited this smart ship simulation center in Brisbane. Some of us got to drive a carousel tug. Was that one of yours?
Yeah. No, of course, we are in very good contact with Peter. We've got our own force simulator ourselves as well, and we developed the simulation version of the CRT well before we had the actual vessels. And we know, because we've got the actual vessels, the same ones, we know how the simulation relates to the real thing. And actually, it turned out that the simulation, the real thing is even better than the simulation. So yeah.
Thank you.
I might speak up, Julian, and thank you for your presentation, and thank you for coming to talk to the group. Just to give a bit of background, I have been fortunate enough to actually have visited on board this tug. Julian invited me together with Mark to one of the smart ship simulations that was hosted as a sales pitch for the carousel tug, because I at the time didn't know anything about it, but have, you know, in my role at work, have some operational responsibility for a certain number of tugs that do escort operations, and some crazy kind of indirect towing and very high line pull forces, but do that with traditional Robert Allen designed ASD tugs, and we do indeed see these high heeling forces, and we do see deck immersion and deck edge immersion, and you know, there are plenty of videos on YouTube of deck edge immersion going wrong and actually girting happening, and people have lost their lives. So for me, it was a very, very interesting proposal when I, you know, understood the physics of, well, now I've moved my towing attachment point to the side of my vessel, and not only am I not creating a heeling moment anymore, I'm actually now creating a righting moment. So I get to a point of equilibrium where, in fact, in a complete loss of power, the tug will just get dragged along behind the ship and will not get capsized. And I think, you know, to get to the nitty gritty of it, you know, Julian sort of glossed over it, but the position of the ring on the hull is slightly offset towards one end to you know, to give an attitude of drag, if you like, isn't it, Julian? So that if the tug does end up getting dragged along by the ship, it does adopt an attitude that breaks the ship, and it solves its own problem, because now, well, you've got a problem, and what do you want to happen? Well, you want to stop the ship, and how do you stop the ship? Well, by applying a stopping force in a dynamic manner. So that's also a very elegant solution to a problem. And I think so. Yeah, back to the beginning. I was fortunate enough. Julian and Mark have also flown me from Marseille up to Antwerp to go and spend an afternoon on the Nova Tug and actually see it in action. And I can attest to the fact that it's a very elegant design. The winch is also very smart and clever. I don't know if you want to talk a little bit about the winch, Julian, or if there's an interest in that. But one thing I will just touch on, and you raised it, and I think it's very relevant to naval architects as a whole, is that, you know, yes, you don't have a point load on your vessel anymore, but you still have a point load on the ship. And the bollard, the mooring bollard in particular, is of critical importance to shipping. And I think as naval architects, it's probably something that is overlooked. We all understand the resultant force on a structure with a you know, let's say a pulley or a sheave, for example. What people sort of forget to think about is the fact that if you've got a tow line of a tug that's got an 80-ton force on it, for example, that's going around a fair lead onto a bit, that now you've actually got a force multiplier on that fair lead. So you might have 80 tons on the tow line, you might have 80 tons on the bit, but you've actually got 150 tons or more on the fair lead. And what we actually do see, and you know, with some of these large tugs that can create some of these large tow line forces, we actually quite regularly pop fair leads off ships. We actually pop roller fair leads off ships. We have Panama fair leads that go skating across the deck and wipe out the guardrails and half the stern of a ship, because we have tow lines that have a breaking strain of 300 tons. But the fair lead is only rated to 50 tons.
Yeah.
And it's actually not the fair lead that fails in most cases. It's the deck. So the deck is only attached by a few, you know, intermittent welds underneath structure. And of course, the naval architect in their wisdom thought, oh yeah, it's fine to just put a fair lead on there and we won't put very much structure underneath it. Maybe we put a bit of extra deck plate thickness. And of course, the deck plate peels off the structure, and the structure wasn't adequate in the first place. So it's the same description that applies whether it's a container ship, a bulk carrier, or you know, a pleasure yacht or a passenger ferry. Actually, attention does need to be paid to the mooring structure to ensure that it's actually adequate for what it's going to see. So that's just a point that I picked up on there, Julian, out of your presentation, that's really relevant to our field as well.
Yeah, no, I agree, Robin. And you mentioned that it was a sales pitch. Well, really, it's we want to spread that it exists, but you are very right. The chain is only as strong as its weakest link. And but the good news on that is that once this possibility starts to become known, it is not hard for a ship to strengthen these things. So it's the easiest solution that can be solved is to say, okay, so you need a couple of very strong points where you actually attach this thing. And in fact, in tankers, you've got an emergency tow point, right? So from some of the, and that shows that it's just perfectly possible to, because it's just steel, and it's just indeed paying attention to the detail at that point of the ship design, to say you need a couple of points where you can actually pull a lot of with a lot of force, because indeed that is a point load, but it's easily solved. It's not like it's a conundrum that cannot be solved, but it needs to be understood by everyone that, yeah, we need to look at that too. And in that sense, we're also talking to the classification societies, because we think that it's wrong for them to sort of not update their criteria for these large ships, to say, well, it needs the bollards on deck need to be a lot stronger, and it's not expensive, it's not impossible, it just needs to be regulated too. Okay. And yeah, I welcome everyone. Mark sitting in. We have this available in SmartShip in Brisbane to play around with. And if you can convince Peter that he'll let you play, then we're fine to sort of, because it's not about selling. I know that you're also not clients, but it's so important that this community understands that this is possible. And then indeed starts talking about, well, what else do you need next to this very powerful tool.
I think it's also elegant. You skipped over the slide with the FEA of the Voith propulsion system as well, Julian. But I'm sure there's probably a bit of interest in this room around the propulsion system.
Well, the most interesting thing there is that I was at Damen on Monday too, and everybody is always complaining about these Voiths because they are so expensive, and then my answer is always, well, we didn't buy expensive kit because we like buying expensive kit. It's there for a purpose, because you control the force on the line with this tug with the orientation of the tug hull relative to the tow line. And if you want to, the big thing with this tug is not to generate high forces, it's to control those forces at all times and to be able to reduce the force when you see it goes up too high. And that means that you have to always be able to immediately turn your tug back in line with the tow line vector. And a Voith is a propeller that can actually deal with varying inflow without unwanted side effects. Because once you go through the water at a relevant speed, a normal thruster is a standing propeller in a tube in its
nozzle.
Yeah, in its nozzle. Yeah, thanks. English is not my. I can deal with English, but yeah, sometimes it takes a bit of time. But the nozzle is also a rudder when you go through the water. So when you turn the nozzle, there's also a steering effect, and that might be that you do a sort of a paper clip. When you want to turn back the hull to reduce the force, the first thing that might happen is that you actually increase the force of the line. And that is, but the other thing, very interestingly, is that with these Voiths, and this again harks back to the electrification, the next step of reducing power is that you can actually charge with the Voith. A normal propeller cannot do that because the flow speeds of the water are not high enough relative to the surface of a normal propeller. So the revolutions of a normal propeller are also much higher than that of a Voith, and that's because the Voiths have a lot more surface. And because you've got a lot more surface, you can actually start charging like you would do with your electric car when you're braking. The kinetic energy is not lost in friction heat. It goes back into the battery by basically through software turning the poles and making the motor a generator. And this is actually also, at least in theory, possible with a Voith. And that is what we're now also working at in order to make the electrification even more interesting. And yeah, so the Voith, or the cycloidal propeller, I should say, because it's not, we don't have shares in Voith. That's not the point. There's a very good reason to apply cycloidal propellers with this to combine this technology with that. And the other thing is, Robin, I heard you say about the position of the ring, and that is also something that is quite well understood by us, that the position of the ring on the tug is also a function of what is your main purpose with the tug. If you want to steer as an escort tug at high speeds, the ring should be more forward, and if you want to do more braking, the ring should be more in the center of lateral resistance of the hull as it is, and that can go in. You're completely free to sort of think of these solutions.
So just expanding on your thought there around the energy absorption from the water, if you like, of the cycloidal propeller as a generator.
Yeah.
How does that affect your overall energy picture? Are you actually creating more braking force or torque?
No, you're actually, your energy picture is that from a typical 40-45% over the total cycle that you could get from a typical tugboat profile of mobilization, dynamic jobs and static jobs. Over that cycle, we now achieve, with a captain that really understands the system, we now achieve about 40% of energy savings. You can do another step like that when you can actually, in the dynamic functions, that you can absorb the energy. It would need for Voith to change the management of the blades to software rather than a kinetic arm. So it would need for Voith to, but they understand it. We've done the first calculations about it. They know this can be done, but they were hesitant with the investment. But now we show them that there's actual value, and of course the resistance of the system when you charge will also go up. So then you can actually brake without even turning sideways. But the braking force will not be the big thing. The energy absorption will just help you save more energy. So it will again reduce your capex on your tug because you can do with less batteries, because you can recharge during the job, which is basically again what we do with cars. You know, the breakthrough of the Prius was software. It was software recognizing when to accelerate and when to decelerate. But of course, with a car, you're not drifting all the time. So it's basically a one-way sort of movement, and it's just turning the poles on the machine to either charge or accelerate, to raise the resistance electrically and then charge the batteries, because it's just a wheel that turns one way. And here, of course, you've got more than one direction. So it's a little bit more complicated, and there is some loss. There's more loss too, of course, of the kinetic energy, but it is a viable route, and we are very confident that we will be able to take that as the next step in electrification.
So
Julian,
Sorry,
go on, Robin.
But I know this coming from a lawyer.
Well, the physics is not that hard, Robin. You know.
Oh, sorry.
So particularly the safety aspect sounds like this, you know, the what do you call it? The dynamic tow point thing is just almost seems like the total way of the future. Is there going to be some application still for standard tugs, or do you think this will pretty much be it going forwards?
Well, again, the biggest thing is fighting the lawyers, because I've once said in a presentation in Singapore, rules are the real weapons of mass destruction. It's once a rule is there, it's very hard to change it. And as a lawyer myself, I say, well, but it's not hard because it's just paper. You just need to understand that it has benefits. And again, in this webinar on Monday, these people were actually explaining that the Suez Canal is 330 meters wide, but the deep part of the canal is only 150 meters wide. This type of vessel is 59 meters wide. So the margins are just too slim. And I say, well, you need tools to up the steering of that sort of thing at this dubious speed range. And there is no tug attached during the canal passage, because there's no tug that can actually do anything now existing that can actually assist that ship from keeping its lane. And I say, well, our tool can. This is what it was designed to do. And so it's not even about changing something that is done today or eating into some industry. This is added on. And the only viable alternative is to make the Suez Canal 4 times as wide, but that is a very costly affair. But they were actually, I mean, for me, it was mind-boggling because they were actually considering doing that because it's 19% of world trade. They say, well, but this is a lot cheaper. But I've had, also in Australia, I've had Kafkaesque conversations. You know, the port of Melbourne, they wanna dredge the turning basin because the next generation of container ships that need to go in there don't fit, they say, but they don't fit because there's tugs front and aft. And we say, well, our tug can assist within the length. So you don't need, so you can take that next step. I mean, it's got limitations too. You can't turn a 400 meter ship in a 350 meter basin. That's clear. But the limitations now are the tugs, not that the ship itself already fits. It's that they, and then they say, well, but we've got budget 200 million Australian dollars for dredging. We don't have $20 million budgets for tugs. I say, well, but that's insane. That is the sort of conversations I'm having.
That sounds extremely frustrating.
Well, it's also fun, eh, Mark?
So your prototype was retrofit to quite an old tug. Is it something that's viable to retrofit to existing tugs, or is it not really worth it without a specific hull shape?
Well, no. Any tug will benefit from this carousel ring because it can't capsize, and you can, to a certain extent, capture the benefit of it as a wing through the water, like but retrofitting is quite costly because you generally have to deal with exhaust pipes and it has to fit all within that ring, because that you can't have an exhaust pipe outside of the ring, let's say. That's one. And two is that if you really want to benefit, you have to understand where the real potential lies, and that's in higher speeds, because it's also elegant in the sense that the steering and the braking will go up with the speed, so it gets ever more effective. And normal propellers are just not good at sideways inflow. And so a retrofit is always limited to 6-7 knots, because beyond that it becomes too hard to control the forces. And the prototype that we built was effectively sourced for this job, because it is already a tug that has inline propulsion rather than side by side. So the prototype is 29 meters long, but not even 7 meters wide. That's also why I have these conversations with these class societies, and they make me nuts, because I say, well, we've done 10 years of real jobs with that tug, never ever been in trouble, and now you're telling me that I can't go narrow? You're just arguing with physics. It's stupid. Of course, that doesn't make me much friends neither. So.
That's very interesting. So perhaps specific tugs that have already got voice, or particularly if on the odd chance that they're inlines or something, they might look into it, but probably your standard propeller-driven older tugs wouldn't really entertain it.
Well, in fact, that would be my best bet to indeed retrofit, but then you've got a very old, like we did, because you can make a very old, outdated in the sense of bollard pull tug relevant again, because again we put a lever of 7 times the static bollard pull on that tug. And you can do amazing things with it. There's lots of videos, and that's a straight shaft propeller driven turning nozzle at the back and a retractable Aquamaster thruster at the front. So and we've done amazing things with that. We've proven that like for like, because we've got a similar tug without the ring. So we bought them, 4 of them, only to retrofit one, but we did tests with fuel efficiency, and then we showed that it saves, like for like, it saves 45%, and then the one with the ring was of course dumbed down because the other one could only do 21-ton jobs. So we couldn't get jobs that are in where this thing really shines. So but it's more fighting regulation and fighting than technology risk or de-risk, because it works. I mean, the things that we built show that they work, and people from all over the world come and visit them. Well, not now in Corona times, but they're all amazed. I mean, maybe Robin can say something about that, but indeed, we took from the ITS in Marseille, we took a group of people who were interested to a real job in Antwerp from Marseille, and it's just escorting all the time, basically, also at relatively low speeds, 5-6 knots, and you get a real effect on your efficiency from 1.5 knots through to 2 knots through the water. It's water is really strong. I mean, also the Ever Given. What took the Ever Given off is the water, is the ebb tide flowing out, pushing against this ship over 400 meters with 15 meters draft. That is real force. And if you, yeah.
So, sorry, one last question from me. Assuming that you can get the regulators across the line, I'm imagining that a little bit extra gear on board is going to make the carousel tugs a bit more pricey than a normal one, but with a 40% energy reduction, you're going to be recuperating that cost at a pretty good rate. So what's your sort of return on investment for the carousel tugs?
Well, the carousel tug is not more expensive than any other Voith tug. What sets it apart is the Voith.
Oh, okay.
Because Robin already mentioned the winch. We've got our own winch solution, because on that sort of height on deck, we don't need, I mean, it's classed for 200 tons safe working load. So you don't want a typical render recover 200-ton winch weighing 50 tons turning around on that plane and that high up on the ship. So we devised our own solution, which is a winch that has one drum, but with 2 parts, one centric and one eccentric. And if you want to hold high forces, you put that winch in a position where you lever the brake of that thing to 200 tons. You basically can raise the 5 times the brake force. And it doesn't do render recover because you don't really need to. We've been having lots of questions from Australia, particularly in how does it operate in waves. Well, it's like a surfboard. You can actually look at the waves. A good captain can work with the waves and keep the line without heaving in or paying out all the time. Just keep the line at a steady length and turn the hull with the wave and just surf the wave. That is, yeah, you are very free with this machine to do an optimal job. I mean, the waves don't come in 3-second frequencies. It's you can feel and see and measure, and the system can also help you. There's wave prediction algorithms now. There's basically a standard DP system, a little bit adjusted, can already help you keep a force to a steady sort of 5 tons more or less in the wave without even changing the length of the tow line. And the fact that we've got this one drum with these 2 parts. The winch itself weighs 7.5 tons, and it's counterbalanced on the other side by its own hydro motor.
There you go.
To put that into context, I'll correct Julian a little bit there. A 200-ton render recovery winch is not 20 tons, by the way. It's 40 tons.
No, did I say 20? I meant 50. Too heavy.
It's big. Let's leave it at that.
Too heavy to be turned
heavy,
around on that height on a tug.
Yeah.
Because of course the fact that it turns means that it moves. And you get a sort of a that would be crazy for your stability too. To have 40 tons move around all the time on deck. It's like a very, very big deckhand.